approach in the emotional impact of movies task. This is work I've done with my co-authors Ting and Gautam. So to motivate our approach, we're focusing on the first subtask of the challenge. Hold on, let me just mute the mic in the call because I can't hear myself. Is it possible to mute the mic on your side?
Oh, you want us to mute the mic?
Yes, please.
Mike is by the hang up button. Mute is by the hang up button. You can also do it.
This one, right?
Yeah.
Oh, yeah.
Oh. Oh, thanks a lot. Okay. So we approached the first subtask of the challenge based on the observation that emotions felt during a movie likely depends on past information. So to model this temporal information, we use models such as recurrent neural network. Furthermore, the image space is high dimensional, which is why we obtained lower dimensional representations by using pre-trained feature extractors. Another observation is that the self-reported emotions in this dataset vary smoothly over time, and our regression models often had higher frequency signals, which we smoothed using low-pass filters. Our final observation is that most of the movies are human-based, and a lot of the frames contain faces. Therefore, we use face features to help with our regression models. So we approached the problem as a multivariate regression problem. Basically, we wanted to model potential correlations between the two output dimensions, and we used late fusion of our 3 input modalities to achieve this. So I'll just go through what we did when you showed modalities in turn. So for image features, we extracted image frames from the movies at 1 frame per second, and this is fed into an inception-based network, pre-trained on ImageNet. The image features are fed into our temporal model, which is then goes into our regression model. In each frame of the image, we also extracted the 2 largest faces in terms of area. And for frames with less than 2 faces, we padded this vector with zeros. This goes into our inception-based model, pre-trained on a faces dataset, and the face features are fed into a separate temporal model, which then goes into our regression model as well. Audio modality, we sampled the dataset we sampled modality at 16 kilohertz model. We compute the male spectrogram, which then goes into our BG-inspired model called audio set. These audio features are then fed into our last temporal model, which also goes to our regression model. So to go into more details on the methods, we first extract the features in each modality using the larger pre-trained networks in order to reduce the dimensionality of the features. For our temporal models, we tried LSTMs, GRUs, as well as TCNs, temporal convolutional nets. For the LSTMs and GRUs, they've shown to be pretty effective at sequence modeling tasks, and we use the sequence to 1 setup of these networks with the input sequences of length 10 seconds, 30 seconds, and 60 seconds. For the TCNs, we use the encoder-decoder setup, which has been shown to be effective for generic sequence modeling tasks, as well as for human action recognition. We trained separate temporal models for each of our modality. So to speak more closely for the recurrent model, since that's what we use in our final approach, we use late fusion, which concocted the final state from each of the recurrent models. Then this concocted vector is fed into our regression model, which uses mixture of experts. For our mixture of experts, we use logistic regression experts with a softmax scaling network. This regression model predicts the valence arousal jointly, since we want to model potential correlations. We post-processed our input vectors to have 0 mean and unit variance. And we post-processed our regression outputs, as discussed earlier, using a low-pass filter. In this case, we use the Butterworth filter. For regularization, we used to reduce the effects of overfitting, and we use L2 regularization, which forces the weights to be smaller, as well as dropout and bacheloralization on the activations in the network. Our validation set consists of approximately 30% of the data, and for all of our experiments, we used the Atom Optimizer to minimize the cross-entropy loss between the ground truth labels and our predictions. So for our results, all of the runs here are based on the GRU with a mixture of experts for regression. The differences between the runs is that in run 1, we removed our regularization of dropout and rationalization, and this is trained on the whole data set. In run 2, we enabled dropout and rationalization, but this is only trained on a subset of the data, and this does much worse than run 3, which has dropout and rationalization enabled, but trained on the whole data set. The difference between run 3 and run 4 is that run 4 has a different random initialization of the model, as well as it stops later than run 3. So training longer seemed to help our models out more. In run 5, this is an average over all of the runs. So to discuss results more closely, we note that face features in the scene could capture information for predicting expected self-reported emotions, as that using face features helped out our validation tests. The sequence to one recurrent model also worked best with 60-second input sequences versus 10 seconds or 30 seconds, the shorter ones. This suggests that longer scenes are more informative than shorter scenes, and perhaps even longer input sequences may be helpful. Another point to discuss is that for our tests, recurrent models perform better than encoder-decoder TCNs. Additionally, averaging different runs helped reduce the mean squared error on the test set. However, this did not improve correlation, and our best correlation, as shown earlier, is from run 4, where we are using rationalization during inference. So to be more precise, what we're doing here is that we're using the test batch statistics instead of the trained statistics to normalize the weights during inference. And the effect of this is that increases variance of our predictions, since our predictions would depend on how the test set is batched. But this, using the batch statistics can be helpful when the trained statistics do not generalize well to the test set, seems to be the case here. And this may be due to the small size of the data set. So in conclusion, our approach uses a late fusion of image, face, and audio features with GRUs and mixture of experts. Temporal information, well, is definitely useful in predicting self-reported emotions in movies. And additionally, we need more investigations for broader conclusions on recurrent models versus TCNs for this task, since we only investigated one setup of the TCNs, the encoder-decoder TCN, and many more setups are possible. Additionally, when output labels very smoothly, as in the case here, it may be useful to attenuate the higher frequency signals using a low-pass filter for regression model outputs. And finally, other ensemble methods should be investigated for this task, since we only used averaging, and there's also bagging or boosting, which could help the performance further. So thanks a lot for listening.